Okay, so welcome everyone for the final talk of the series, CMI seminar series. And today we are very happy to have Utsav Choudhury from ISI Kolkata, and he'll speak about unstable A1 homotopy theory and few commutative algebra questions. Utsav, please go ahead.
Yeah, thanks, Krishna, and thanks everyone else who are listening now. Uh, so, uh, I start with the kind of spaces that I am interested in and why I call it competitive algebra space. So for instance, K is a field. So our case, most of the time it will be complex numbers, field of complex numbers. So and A and K will be spectrum of this polynomial algebra in n variables kx1, x2, xn. So as we all know that this is a topological space. You can equip this set with the topology. It's called the Zariski topology, and an affine K scheme. So this A and K will be called this A and K will be called an affine n space, and an affine K scheme, which is different from an affine n space. So affine K scheme is a closed subset of this kind of A and Ks. That is, it is vanishing locus of polynomial functions f1 up to fr. So in particular, an affine K scheme is of the form spectrum of kx1, x2, xn modulo I. So it's like zero locus of these elements inside this ideal I. And then the morphism between affine K schemes correspond to morphisms in the opposite category of K algebras. So in particular, K algebra homomorphism, the opposite category in the sense that K algebra homomorphism, the maps in the affine scheme will be in the opposite direction. And in this regard, we say that whatever I say about affine scheme, these are actually problems of commutative algebra. So for instance, there is this example. I take xyz modulo x minus gyz, a polynomial and yz and x minus that polynomial. So this is isomorphic to polynomial ring in two variables. So spec kxyz modulo this thing, this ring, spectrum of this ring is isomorphic to A to K. So affine to space over K. So now the question is that find out, how can you say, after if someone gives you kxyz modulo x minus gyz, and you have to do some algebra to say that this is isomorphic to k t1 t2. The equation can be something really non-trivial. Then how do you do like really tricky algebra, commutative algebra, to say that whether this is isomorphic to nk or not? In particular, two algebras to show that they are isomorphic is a very difficult problem. So one needs to find out invariants or obstructions to single out affine space among all the affine K schemes. So in particular, one needs to find out um, uh, invariants or obstructions to single out polynomial algebra in some variables, say n variables, from all finite type K algebras. And another question that we have in mind, or I have in mind, is this x times a1 is equal to n. This is a really stupid question that can we cancel out 1 from both sides and make it x isomorphic to n minus 1. Though it looks very stupid, but this question is very much related to several questions in affine algebraic geometry. One of them, this Jacobian conjecture, and all these things are closely related to each other. So now obstruction 1. So the first obstruction is algebraic topology. So since we are working with k equal to c, complex number, so if I take a smooth affine C scheme, so it's given by zero locus of some polynomials. So if I take smooth, so then the complex point will be a complex manifold, and complex manifold being a honest topological space, you can do algebraic topology on it. So you can talk about homotopy groups and homology groups. And then it turns out that suppose X is isomorphic to Cn as varieties, affine varieties, then Xc is contractible because C is contractible. The complex line or this is like the real plane R2 is contractible. So homology and homotopy groups are trivial. So homotopy groups are invariants or homology groups are invariants obstructions to detect affine space. So if you get some smooth affine scheme whose complex point is not contractible, then it is not possible for that to be uh, uh, to isomorphic to Cn. So now the case in the lower dimension. So dimension 1. So of course dimension 0 case is just point. So point is of course every point is point. So there is no problem with that. So dimension 1 So the only smooth connected affine complex curve with Euler number 1. Euler number is this alternative sum of H0, rank of H0, then minus rank of H1 plus rank of H2, and then this goes on like this. So the only smooth connected affine complex curve with Euler number 1 is A1C. So how do you prove that? It is that because any smooth affine complex curve can be completed to a genus G smooth projective curve by adding k many points, and then the Euler number, which is this Ex, this is 2 minus 2g minus k. So this forces g equal to 0. So genus 0 smooth projective curve is P1 or CP1 and k equal to 1. So x is a curve. You attach 1 point to get CP1. So x has to be A1C. So this is the lowest dimension case, which is the easiest one. Then even starting from dimension 2, it becomes difficult. So anyway, so we also get cancellation in dimension 1 from the previous identification, because all these things, so what is the meaning of the cancellation? Suppose I have a dimension 1 smooth affine scheme such that A1 times that scheme, so x times A1 is isomorphic to A2, then x isomorphic to A1. And the proof is precisely this, that A2 has Euler number equal to 1. So x times A1 is A2 implies x times A1 has Euler number 1, and Euler number is homotopy invariant. So x times A1 has same Euler number as x. So x has Euler number 1 and it has to be smooth connected affine complex curve. So we get this cancellation. So now in P2, so algebraic topology not enough. So in case of surface, so this is the first example of a surface. Of course, Ramanujam wrote this really influential paper and one of the most beautiful paper I have ever read. This Ramanujam's characterization of C2. So there he gave an example of a surface which is topologically contractible but not isomorphic to C2. Isomorphic in the sense it is not polynomially isomorphic to C2. That is, it is not isomorphic, it's algebraic varieties. So in P2, so the example is as follows. You take in P2 a cubic with a cusp and a non-degenerate conic, and such that C1 and C2, this two cubic and the conic meets at P and Q, such that P and Q are simple points on cubic. So it cannot be the cusp P and Q. So they are simple points and different from the inflection point of the cubic, so that if you remove this inflection point of this cubic, it behaves like the additive group GA. So you can have these 2 points, and also you can actually prescribe the intersection multiplicity. So intersection multiplicity at P is 5 and at Q is 1. Okay, so you have this picture, and what you do, you blow up at Q. So where the multiplicity is 1, you blow up that point, you get a projective variety blow up QP2. And from there you take the proper transform of C1 and C2 and take them out. So this is your X. And because of blow-up formula and this duality in cohomology, blow-up formula and duality in cohomology, what you get is that the smooth affine complex surface X is topologically contractible. And by this famous paper of Mumford, or famous work of Mumford of combinatories of divisors on a smooth projective surface, Ramanujam was able to show that this X that you get, you can blow it further. I mean, this blow up QP2, you can blow it further such that the locus is outside of this X. So you can blow this thing further and such that the locus is outside of X. And then in that blow up, after such certain amount of blow up, then you can make X is sitting inside some smooth projective surface such that the complement of X is normal crossing divisor. So the geometry or whatever the combinatorics of that will give you that this X as a topological space is not simply connected at infinity. So now I come to the main theorem of Ramanujam, which is the most surprising theorem, because here we are just using these two following properties. So if we have a smooth affine dimension 2 complex variety, it is topologically contractible and it is simply connected at infinity. So these two properties are given. Then it is isomorphic to A2C. So it is an if and only condition, because A2C of course satisfies these two properties. But if some topological some smooth affine dimension 2 complex variety satisfies these two topological condition, then it is algebraically isomorphic to A2C or C2. This is the surprising part. And this was the first thing that actually says that probably topology determines many things in affine algebraic geometry. So next, Gurjar showed that the cancellation hold for surfaces using Ramanujan's result that X smooth affine complex surface such that A1X is isomorphic to A3C, then X is isomorphic to A2C. So you can cancel out A1 from both sides to get X is isomorphic to A2C. Okay, so then Gurjar in particular, he showed actually, I mean, actually there's this recent paper by the father Gurjar and the son Gurjar, which shows that in particular we don't even need contractible, we need that there exists one smooth completion which has genus 0 and of course simply connected at infinity property. Okay. And then topological, I mean the statement is this Ramanujan's characterization actually shows that a smooth affine complex surface X is isomorphic to A2C, polynomially isomorphic to A2C, if and only if the complex point is homeomorphic to C2. So this is the beauty of Ramanujan's result, and that actually was the most influential thing for me to ask this kind of question. I mean, my understanding of or my motivation comes from purely topology, and then the topological just classification of algebraic affine algebraic geometry. And so this result was the starting point, and I wanted to ask the same kind of question if I increase the dimension. Before presenting the main question that I was interested in, or the kind of methods that I was interested in, let me give you another obstruction theory, or another obstruction for, or before that, okay. So let us give us some example of topological contractility. So Kraft, Ashok and Doran, they showed that in higher dimension, that is dimension greater than 2, there exists family of contractible smooth affine schemes, that is arbitrary moduli of smooth affine schemes, not isomorphic to affine space. So each one of the whatever objects that the moduli classifies, they are not isomorphic to affine space, but each of one of them are contractible smooth affine schemes. And such example arises as quotient by unipotent group action. So you can see that this simple question has so many different flavor of mathematics coming into picture, and so many very weird and I would say very random things. So for instance, unipotent representation theory or unipotent action is a very it's not that systematic compared to say reductive representation theory of reductive groups or reductive group action. So so such examples arise as quotient by unipotent group action. And then Petri and Tom Dick and Zeidenberg, Kaliman, they showed that in higher dimension, that is dimension greater than 2, there exists family of smooth affine schemes, each diffeomorphic to affine space. Diffeomorphic. So it's more than homeomorphic. It's even diffeomorphic, but this family of affine schemes is diffeomorphic to affine space. Okay, the sentence is not complete. It exists family of smooth affine schemes is diffeomorphic to affine space, but not isomorphic to affine space. So not isomorphic, but diffeomorphic. Okay. So now another abstraction, that is log Kodara dimension. So I won't go to the definition of log Kodara dimension. If you know Kodara dimension, then log Kodara dimension is some sort of like you take care of the Kodara dimension of the compactification and the boundary. So this kind of thing are called log Kodara dimension. But I mean, anyway, so I will give you what is the meaning in this setting. So Miyanishi showed this is another description or another classification of C2, that suppose X is spec A, smooth affine complex surface, such that the ring of invertible regular function is precisely C star, the constant minus 0, so C star. And A is a UFD, that is a factorial ring, and log Kodara dimension is minus infinity, then X is isomorphic to C2 as varieties. So what is log Kodara dimension? So in the case above, log Kodara dimension minus infinity means there exists open set inside X of the form C times A1, where C is a curve. So dimension 1 smooth curve times dimension 1 smooth scheme, C times A1 sitting in as an open set inside X. And using this characterization, one can also prove cancellation for affine surfaces. In fact, the first proof of cancellation for surfaces came because of this Miyanishi's characterization. So now, so in higher dimension, what happens to log polarization in higher dimension? Of course, if I take the y to be the Ramanujan surface, and I take x equal to y times a1, then x satisfies all the properties mentioned above. In particular, y satisfies these two properties. A star equal to c star and a is factorial. And log polar dimension minus infinity, because you are forcefully putting an a1 inside this x. So there are a lot of affine lines sitting here, and y is in particular rational. So there is this log polar dimension minus infinity means precisely that you have this a1 and some rationality. So then x satisfies all the property above, but x cannot be isomorphic to A3. Why that is the case? Because if x is isomorphic to A3, but then by previous thing we know and cancellation hold, so Ramanujan surface times A1 is isomorphic to A3, so y has to be isomorphic to A2 or C2, but then Ramanujan showed that y cannot be isomorphic to C2. So this is a really nice bit of mathematics and very interesting bit of mathematics where combinatorics and unipotent group action, up to now, unipotent group action, combinatorics, and geometry, all of them, and of course now the algebra part will come. But anyway, so all these things come into picture. Okay, so now G action or unipotent group action. So G action. So this is actually algebra plus some sort of representation theory. So again, assume characteristic k equal to 0. So if X is an affine space in the sense that it's isomorphic to some A and K. So then there will be lot of G action. In particular, the following two things will be true. G action means that GA is the additive group, say spectrum of Kx, but then spectrum of Ks has an additive structure. So so A plus B. So for instance, if you take C with the additive structure, complex number with the additive structure, so this gives you a additive group structure. So this GA is GA is A1 with the additive group structure. So this is the unipotent group. In particular, the following two things will be true. So if X is affine space, one is that functions of x which are invariant under all g actions are precisely the constant function. So what is the meaning of this? That if I contract all the orbits of all the g action, then the space should be same as point, which is the same thing, right? I mean, if x is an affine space, I mean, if you can given any 2 point, there is an orbit passing through them. So you can always contract, or not given any 2 point, take the origin and take any other point. You can always contract that point to the origin. So that if I contract everything to the point, then I just get constant function. So this is precisely the statement that is given here. The functions of x which are invariant under all g actions are precisely the constant function. This is called the Makar-Limanov invariant, which is a very important invariant, and it is algebraically it's possible to compute this thing. So Makar-Limanov and after that many others, they came up with different computation. And of course, there exists at least one free G action. Of course, if X is say A1, there exists a G action that is A getting mapped to A comma T getting mapped to A plus T. This action is free. So just additive action. So this action is free. So there has to be at least one free G action. So G action corresponds, so now the algebra part comes. So G action corresponds to locally nilpotent derivation LND. Short form is LND. And the last statement is equivalent to the existence. So last statement means that there exists at least one free G action. The last statement is equivalent to the existence of a LND from OX to OX and an element A inside OX with dA equal to 1. So what is a locally nilpotent derivation is the main question. So LND on a K algebra, locally nilpotent derivation on a K algebra A is a K derivation, that's a K linear map which satisfies Leibniz rule. That's such that, so now locally nilpotent is the new part. So locally nilpotent means that for every A, there exists a positive integer m, which depends on A, such that if I apply d n times to A, I get 0, where DNA is decomposed n times applied to it. So this is something like saying that I have this a G action. So G action will give me around every point orbit, GA orbit, which is something like A1. So it gives me a tangent direction along that. And if I take a function, this tangent direction, if I take the Taylor series, this Taylor series actually converges after finitely many terms. So the Taylor series is actually a polynomial. So this is the meaning of LND on a K algebra. So for instance, A is KT, then DDT is an LND. Corresponding to the G action is the additive action of A1 on itself. Note that the action is free, of course. And similarly, if I take A, Kx1, x2, xn, I take this LND del xi. So this is a derivation and this is locally nilpotent. Corresponding action is an times A1 to an, where I take this tuple and times t, and the action is that only the ith component, the t, gets added and all the other components remain same. And of course this action is also free, and you can verify that this as del xi of xi is 1. So LND with a slice means that the corresponding G action is free. So these two things are equivalent. So what is an example of a non-free G action? You take A, Kxy again, dy del x. This is an LND, you have to verify. The corresponding G action is A comma B coming from spectrum of this thing, comma T, and then it gets mapped to A plus B, T comma B. Of course, you can see this is not free. Whenever B is 0, even A is non-zero, this will be the same thing, right? So this is not free. So now, how do you use this LND and all this new algebraic obstruction or invariants to classify the A1 or A2 and everything? So any smooth affine curve X is isomorphic to A1 if and only if it has a non-trivial G action. Why that is the case? So the reason is quite clear that if X has a non-trivial G action, that means there will be at least one non-constant orbit. And non-constant orbit means there will be at least one embedded A1. But if X is a smooth affine curve, we can again complete it to get a smooth projective variety of genus G. If genus is greater than 0, then that projective variety cannot have any A1, non-constant A1 mapping into it. But that will also imply that any smaller open set cannot have that. So the only possibility is that X is contained inside P1 of genus 0, and then if I throw away more than 1 point from P1, I get GM or subset of GM, that is C minus 0 or C minus several points more than 0. So, but then all of this also again does not have any A1 mapping into it. So if there exists a non-trivial G action, then X has to be isomorphic to A1, and if it's X isomorphic to A1, of course there exists a non-trivial G action. Okay. So, but then main problem is that Makar-Nivanov invariant, the thing that we described before, the functions of X which are invariant under all G action, these are called Makar-Nivanov invariant. These are not functorial. So this is a problem yet not being fixed by the algebraist. So for an affine surface, trivial Makar-Limanov invariant implies the surface is A to K. So this is one characterization of using this Makar-Limanov invariant to one characterization of A to K using Makar-Limanov invariant. And using this one also, this one can also get cancellation, because of course we know that Makar-Limanov invariant is trivial for affine spaces. So if X times A1 is A3K, then you have to prove that X is isomorphic to A2K. So this this can be done. So now Korus-Russell. Korus-Russell, or Russell-Korus, what does this? They constructed a topologically contractible affine threefold X with non-trivial Makar-Limanov invariant, which implies that it cannot be isomorphic to A3, but X times A1 has trivial Makar-Limanov invariant. So there is a hope that X times A1 is isomorphic to A4. It's not yet being proved, but this is one hope that, or people think that this can be a potential counterexample to Zariski's cancellation problem. Okay. So in characteristic 0. So Korus-Russell threefold gave this example of a topologically contractible affine threefold with non-trivial Makar-Limanov invariant, but X times A1 has trivial Makar-Limanov. Okay. So now we'll go to this homotopy, A1 homotopy part. So I don't know how much time I'm left. Okay, I have more than half an hour, so we can go through this construction. And if you are seeing it for the first time, then don't worry if you don't understand anything. I mean, this is just a, you can take it as a black box. So what are the things that we want to do? We start from the smooth category of smooth schemes. So I hope that you know what is a smooth scheme. Smooth scheme will be like you glue affine schemes, but affine schemes will be given by some bunch of equation, and the bunch of equations should satisfy this property. At least when k is algebraic is closed, this on the affine chart, it should be given by this kind of spec of kx1x to xn modulo f1 f2 fr, such that dfp k into kr is surjective linear map for all p inside f inverse 0, where f is this f1 f2 fr from k into kr. So this is like one kind of smooth scheme, then, because this is one basic. You can take this as a definition of smooth scheme. And then not only this thing, so there are certain invariants that you want to classify in a more you want to study in a more systematic way. So this those invariants satisfy something called Nisnevich descent. So for instance, K theory, algebraic K theory, or say Chow group, higher Chow group, Milner K theory, Milner-Witt K theory, all these kind of things that are those are which are related to intersection theory or algebraic K theory. You want to study them in a systematic way. So then all of them satisfy Nisnevich descent. So what is the meaning of Nisnevich descent? For that we need to have, so in general, descent means that if you in a topology, so suppose you have a topological space X, you have information. So if you have a topological space X and you have this open cover UI of X, and you have information of your homology or whatever on UIs, and you want to get information of X, so you want to say that you can glue this information to get information on X. So this is the definition of descent. So for instance, a sheaf condition is a descent condition. Okay. So for that sheaf also you need a notion of topology, and you need a general notion of topology. So Grothendieck topology. So we need here something called a Nisnevich topology. So Nisnevich covering. Nisnevich covering is a bunch of étale maps. So, so a finite family of étale morphism is called a covering family in the Nisnevich topology. If and only for any point in the base there exists some UI here and a point y inside UI mapping to X here, such that the residue field are isomorphic under this morphism Fi. Okay, so this is more restrictive than étale topologies, but in general, I mean, the topology generated by this covering gives a Grothendieck topology on SMK. And then what you have to do is that you start with SMK, and you want to put étale descent. First of all, you want to make sense of what is homotopy here. So you have to enlarge this category to have something called homotopy colimit and homotopy limits. So for this, you have to go to the category of simplicial presheaf. So simplicial presheaf, you can think of, if you are not used to simplicial set, you can think of topological spaces. So simplicial sets are combinatorial way of remembering topological spaces. So what is a simplicial set? Simplicial set is points, lines, triangles, tetrahedrons, higher dimensional tetrahedrons, and how point is identified with boundary points of a line, how lines are identified with the boundaries of a triangle, and how triangles are identified with the boundaries of the tetrahedron. All this information are built in this gadget. So a simplicial presheaf, a simplicial set is this kind of gadget, and a simplicial presheaf is a presheaf that is, it starts with a smooth scheme and gives you a simplicial set. So in particular, you can think of a smooth scheme getting a corresponding to smooth scheme, you get a topological space, but not only the space, you know how the algebraic topology structure of the space, in the sense that what is the combinatorial way of attaching lines to points, triangles to lines, and all this stuff. So a simplicial presheaf is, you start with a simplicial presheaf, and then you need invert something called Nisnevich local equivalence. So there is a systematic way of inverting this kind of thing. So maybe these results are not important here. So maybe I can skip these results. Okay. So anyway, so what you can invert this Nisnevich local equivalence to get this Nisnevich descent. So descent with for respect to this cover. So, and the corresponding resulting homotopy category is denoted by HSK. And then what you want, So once you have done this HSK thing, in this HSK you get new isomorphism. So new isomorphism is this following. So suppose I have a closed point inside X and X is irreducible dimension n, then I will get X mod X minus X. So that this mod is in the category of sheaves. So this sheaf is isomorphic to ANKX modulo ANKX minus 0. So in this HSK, in this new category HSK. So this is yeah. So now comes the A1 model structure. So A1 model structure is the thing that you have already inverted morphism Nisnevich local weak equivalence to have Nisnevich descent. Now your theory also have the added property that it does not see any difference between A1 and point. So you want to localize or you want to invert this kind of map Z to Z times A1. So this is a typical method of localizing. If you are not used to model categories or localization or anything, just think that there exists a black box where which can be used to invert a given set of morphism in a given nice category. So this anything arise coming from simplicial pre-sheaf is a nice category, and if your morphisms are sets, not classes, or at least yeah, so can be approximated by sets, then you can always do this localization or make this morphism invertible. So A1 local objects is the first thing. So for instance, this local thing. So for instance, if you are doing cohomology theory or this sheaf cohomology, first you do this kind of injective resolution, right? Given a sheaf, you take an injective resolution and then compute the cohomology of the global section of this injective object. So these injective objects are precisely the local objects with respect to say Zariski topology if you are trying to compute Zariski cohomology, or Étal topology if you are trying to compute Étal cohomology. So these injective objects are the things that mostly you are, I mean, the geometry is hidden normally in this injective object. So you have to take, normally you cannot take injective resolution, you have to take some flabby resolution or flask resolution, and then if you have a flask or flabby resolution, I mean, you can actually go to an acyclic resolution and then compute cohomology. So there are several kind of resolution for particular cases, and those particular resolutions are the geometry of those cases. So here also in the A1 local objects, so those objects which are say flask or acyclic in this setting. So these A1 local objects are those which does not see any difference between a affine line and a point, and geometric examples are precisely curves of genus greater than 1, because we know that a curve of genus greater than 1 cannot have a non-constant affine line mapping to it. And abelian varieties are examples of A1 local objects. Any vector bundle projection map is an A1 weak equivalence. Okay, A1 weak equivalence is something which is more general than this kind of projection. So any vector bundle, for instance, because vector bundle locally, even Zariski locally, so Nisnevich locally looks like this kind of projection, right? So, and then Nisnevich descent plus this kind of maps are invertible will imply that any vector bundle projection map is an A1 weak equivalence. And the resulting homotopy category is denoted by HK. So in any case, so we have this special property here. So there are, I mean, unlike the usual algebraic topology, there are two spheres here. One sphere is the simplicial sphere, where you take the usual simplicials delta 1, the interval, and then identify the boundaries. So, and then you can smash this S1 S with itself n times to get the sphere in the sphere. But then there is another sphere S1T, which is GM pointed by 1. Okay, and then SNT will be defined as S1T smash n times. So one of the very important, or one of the most important thing in unstable A1 homotopy theory is that this Thom isomorphism. So what is this Thom isomorphism? First I start with a closed immersion of smooth schemes Z2X, and then the Thom space of this closed immersion is just the quotient X modulo X minus Z. Okay, so this is what you do in topology also, in differential topology. So X mod X minus Z, and then also you can take Thom space of a vector bundle is given by you take the zero section, and Thom space of E is the Thom space of this embedding X inside E, Thom space of S0. Now, if I take Z2X, which is a closed immersion of smooth scheme, and N normal bundle of this embedding, then Thom space of N is isomorphic to Thom space of the closed immersion in the A1 homotopy category. So this is one of the most important result. I mean, the reason why I mention it is just to give you a flavor that there are more non-trivial things happening just after introducing this simple kind of relation that A1 is equal to point, and you can glue Nistevic locally results to get a global result. So these two relation gives you already so many isomorphisms, so many information. So for instance, you get by the previous theorem, you get the Thom space of zero section mapping to A1 is isomorphic to A1 mod GM, is isomorphic to P1 mod A1, which is isomorphic to A1 S1S wedge S1T, which is isomorphic to P1 comma infinity. So these all this chain of isomorphism which are completely new just because we have these two basic relations. And again, n minus the origin, 0 means origin here. This is also kind of a sphere, but then you see that in case of topology, n minus 0 is the so for instance, a2 minus 0 is s1, or at least homotopic to s1. So n minus 0 should only have in topology this part, but since we are in the algebraic situation, it also have this SNT, the algebraic sphere part also. Okay, so invariance. So this is the invariance that I am interested in. So we are in the situation of a simplicial pre-sheaf, and given a simplicial pre-sheaf, you can associate two kinds of invariant. One is invariant in sets, pre-sheaf of sets, and one in pre-sheaves of groups. So what is pre-sheaves of sets? So you inside SMK, pre-sheaves of groups, you inside SMK, I can take the homotopy classes of maps SISU plus to x comma x, and this is denoted by pi I a1 x comma x after the sheafification. So this is a pre-sheaf, and then I sheafify it, and this sheaf is called the ith a1 homotopy group sheaf for I greater than 0. And if I equal to 0, the Nistevic sheaf associated to the pre-sheaf U mapping to U comma x hk is denoted by pi 0 a1x and called the a1 connected component sheaf. So the spelling is wrong here. A1 connected component sheaf. So there are two things. One is connected component sheaf, which is a sheaf of sets, and then there is this homotopy group sheaf, which is a sheaf of groups. And there is a theorem, which is a folklore. A space X is A1 contractible, that is, X is isomorphic to spec K inside this homotopy category if and only if pi I A1X's are trivial for all I greater than equal to 0. So all homotopy group, including the connected component, is just a single point. So this is what you learn in topology. So this happens here also. Now, the case of curves. So connected component actually is the obstruction there. So smooth projective curve of genus greater than 0 are all A1 fibrant. So only have pi 0 A1x, which is isomorphic to x. So the genus 0 curve P1 has pi 0 A1 trivial but non-trivial higher homotopy groups. In fact, pi 1 A1 P1, which is a sheaf of groups a priori, is non-abelian. So this is the only non-abelian example known and related with the Milnor-Witt K theory. So this is the basic, or I would say fundamental work of Morel, where he computed this Milnor-Witt K theory sheaves and related it with A1 homotopy theory. In particular, presence of non-trivial GM bundle or line bundle will always make the A1 fundamental group non-trivial. So this is again a result of Morel. An affine case will never have higher homotopy groups, will only have connected component. So affine case in the sense affine curves will never have higher homotopy groups, will only have connected component. In fact, curves projective or affine is always classified by A1 connected component. Okay, so this is a very nice situation where if I know pi 0, then I know everything. So if you contrast it with usual topological setting, if you have a curve, if you know that curve is Euler characteristic 1, what does this mean? Euler characteristic 1 means that it is connected, of course it is given, but it also means that H1 is 0. So H1 is 0 will imply that the curve, because the curve, affine curve will cannot have H2. So H1 and H0. So H1 will be 0, the cohomology, singular homology or singular cohomology, whatever you take. And this will give me that it is isomorphic to A1. In this case, actually it is saying that if I have the curve A1 connected, that is by 0 A1 is trivial, then the curve is actually isomorphic. If it is affine, then it is isomorphic to A1. So this is a characterization in dimension 1 using A1 homotopy theory. This is a folklore characterization. Now there is a conjecture of Morel which says that this pi 0 A1x sheaf does not see any difference between U and A1U. So it does not see difference between A1 and the points, a homotopy invariance conjecture. So this conjecture is verified by curves trivially that it's a folklore, so trivially it is verified, and smooth projective surfaces. So this is a great bit of work by Choudhury, Baloy and Sawant. And for general simplicial presheaf, so the general results in this direction, I did it during my PhD thesis. The conjecture is open for affine surfaces, and classification problem for A1 contractible surface is an open problem. So it is not known why. So the main question, what is the main question, is whether A2K is the only A1 contractible affine surface. Okay, so it is not known whether there exists anything other than A2K which is A1 contractible. Of course, A2K is A1 contractible by definition because we have made A1 to be point. So A1 times A1 is same as A1 times point is same as point. So A2K is same as point in A1 homotopy theory. But then, does there exist any other affine smooth scheme or affine smooth surface which is not isomorphic to A2K, but it is A1 contractible? So, anyway, A1 contractibility is an obstruction for both classification and cancellation problem. Okay. So now the singular construction. So singular construction is so now we are coming to the kind of the research that I am interested in, the question. So the question that we started with, classify these affine spaces, and what are the obstruction, new or obstruction that we are interested in, because the previous obstruction had already been exploited. So the newer obstruction is the following. So I start with co-simplicial scheme called this delta dot L. So this, if you don't know what is a co-simplicial scheme, forget about that. For each n, I get a scheme, and this scheme is spectrum of k t0 tn modulo this hypersurface summation ti equal to 1. So this is same as the standard simplicial the standard simplex, n simplex defined in topology, but there you also have ti greater than equal to 0. Here I don't care about whether they are greater than equal to 0 or negative, positive, all these things we don't care. It's just the same, summation ti is 1. And the coface and co-degeneracy is given by following the topological space. So say for instance a face. So delta n algebraic will have delta n minus 1 sitting there, but in actually n plus 1 ways. So how do you get this n plus 1 ways? Because the points here are points inside n plus 1. So there are n plus 1 tuples. So n to n plus 1 tuples, you just make the ith coordinate 0. So you get this face maps. So for x inside SMK, even for any simplicial PC, we get sing x. So x is SMK. So sing x by taking, so it is a simplicial PC. You take u inside smooth scheme and map it to this delta dot alg dot u comma x. So the maps. So for instance, if I take degree n, so simplicial, this is a simplicial set. So simplicial set, the nth simplices are mapped from delta n alg. So this is this guy times u to x. Okay. So there are projective surfaces for which sing x is not A1 local. So these are not the acyclic objects that we are looking for if sing x. So this is a very important for projective surfaces in fact. So Choudhury, Sawant, Baloy, they proved this. So the question is, of course, find out an affine surface for which sing x is not A1 local. So this is also open problem. It is known that sing an minus 0 is A1 local. In fact, it satisfies affine PG problem anyway, so it's not a problem for us. So the main thing, that the kind of thing that we are interested in actually is this. So sing an. So how to classify sing an? So there are these two properties. So an has this property that an is a group, and whenever you have a group, then Sing N will be a simplicial presheaf of abelian groups, because N is an abelian group. The maps to abelian group will be again an abelian, will have again an abelian group structure. So this will be a simplicial presheaf abelian group. So in particular, it will be section wise confibrant, and it is contractible, therefore it is A1 local. So this is a very important observation that we made together with my PhD student, that this is one thing that is not yet exploited. So let us try to exploit this property. So we saw this result. We observed this result by Dublos, Pauli, and Ostaver. It is actually a reformulation of Miyanishi's result, but in a very topological, or I would say in a very A1 homotopy theoretical setting. That a smooth affine complex surface is isomorphic to A2C if and only if X is topologically contractible. So this is a topological property, and Sing X is connected. So this is called chain kind. Sing X is connected means that this, or maybe, so these guys are simplicial set. So like a topological space, it will have pi 0, and I need this pi 0 of this topological space to be connected. This is called chain connected. In particular, this means that any 2 points in X can be joined by a chain of affine lines. So finitely many affine lines. Okay. So this is a very nice characterization that we saw, and then we actually started thinking about how to. So now how to use this result, and also how to use the previous. So how to use this result and how to use this previous characterization of AN. So let us go to what is confibration means. So algebraical. So now this problem is of commutative algebra. So what is the meaning of confibration? Confibration means that for each k greater than 0, suppose we have maps from n minus 1 alg. So this is isomorphic to n minus 1, which is sigma I k to x. So this bunch of maps are given for I 0 to k minus 1, kth one is missing, and k plus 1 to n. So there are this many maps, this is given, such that if I restrict the jth map to the ith phase, and that will be same as restricting ith map to the j minus 1th phase for all I less than j with ij less than not equal to k. So if I have this situation, then so say here dj is given by putting 0 at the jth coordinate. So here to here. So then Sing X is confibrant if for each k and sigma k as above, there exists a sigma from this delta and alg to x. So I can fill up this all this. So these are like phases of delta and algebraic. Apart from one phase, the kth phase is missing in this description. So kth phase is missing, and all the n minus 1th phase has a map to x. Then I can fill up this whole thing to get a map from this. So this is the filling property. Okay. So this is called the Horn filling property, and this is, I would say, that the algebraic Horn filling property is satisfied. And since everything is affine, here x is affine and n minus 1 is of course affine, so then you can write this condition using just K algebra homomorphism. So this is actually becomes a commutative algebra problem, confibrancy of Sing X. So so far it's a lower dimension example, n equal to 2. What does this case mean? That I have sigma 1 a1 to x and sigma 2 a1 to x. So there are these two lines such that the if I evaluate sigma 1 or at 1, so there is a point 1 here, then whatever the point I get is same as sigma 2 evaluated at 0. So there are these two a1 intersecting at a point. Then I can extend, so I can think of this a1 and a1 to be just x and y axis. So then I can extend this to a map from a2 to x. Okay, so this is precisely the confibrancy means. So the question is again, of course, which kind of spaces are confibrant? So for given x affine k scheme, which affine k scheme x, I have Sing X is confibrant. So now I have this new obstructions part. So this will be like the finishing bit now. So look at this following equation: x to the power mz minus y power r minus t to the power s minus x for m greater than equal to 2 and r is greater than equal to 2. Of course, r and s are relatively co-prime. So these are called Chorus Russell threefolds. Okay. So this example that I gave before, or the statement that I made before, that porous Russell came up with a threefold, which is topologically contractible with non-trivial Makar-Limanov invariant, such that x times a1 has trivial Makar-Limanov invariant. This is precisely that porous Russell threefold. It's a family of porous Russell threefold. So, of course, this is supposed, I mean, the algebraists always believe that in characteristic 0, this is supposed to be the counter example to Zariski's cancellation theorem. But then Arvind Ashok predicted that actually XMRS are not A1 contractible, so that they are not potential counterexample to cancellation problem. So that the algebraists, they just feel very sad. But then the algebraist won because Mark Hoya, Krishna, Ostave, Duclos, Fazell, all of them showed that actually they are A1 contractible. So then algebraists have an upper hand now. They can say, that, okay, the hope of Ashok is gone, and algebraists still have a upper hand. Porous Russell threefold still can be a counter example to Zariski's cancellation theorem. At least A1 homotopy theory probably don't tell you whether it can be counter example or not, because A1 homotopy theory, naive A1 homotopy theory, or whatever I1 homotopy theory I described, it might say that of course A1 contractibility is one obstruction. If it is already A1 contractible, then there is nothing else you can do, because using A1 homotopy theory. So it seems that the hope is gone. Hope is gone for the A1 homotopy theory, so the topologist. But obstruction is seeing XMRS A1 local and contractible, is seeing XMRS connection-wise confinement. So these two obstructions are still left, and this was completely overlooked by the topologist. So together with my PhD student, we started investigating this. So suppose one of the answer, if any one of the answers to our question is no, then porous Russell threefold is not a counter example of Zariski's cancellation. Sad. But then the algebraist will think, okay, it's better that we should have both of them to be false. But I also have a good news for the algebraists, that if both of the answer is correct, true, then also algebraists should not lose hope, because then in that case, there is a famous conjecture called the retraction conjecture, that suppose I have x sitting inside, so this x is sitting inside A4. Okay, so x sitting inside A4, and whether I can have a retraction, so x inside A4 and A4 to x, such that the composition is identity. So and x is not isomorphic to A3. Is it possible? So for instance, if I have A3 inside A4, A3 sits inside A4 as 0 section, and then there is a projection map. So this composition is identity. But is it the only example, or there exist other examples? So my guess is that x is, or yeah, so it's a too early to call it a guess, but yeah, I will hope that x satisfy this, the porous Russell satisfy this, that x sits inside A4, but then there is a map from A4 to x, such that the composition is identity. And if this, so when can I prove this? Also, this is a very this is a relevant question. This retraction question, and if both of them has a positive answer, then actually the retraction question can be attacked using algebraic topology. Okay, so now we go exactly what result we have. So these are like not at all results yet, because these are this work still going on this question. So the results are, before going to the results, so we are actually interested in classifying A3. So Nina Gupta and Nikhilesh Das Gupta, her PhD student, they proved that K algebraic closed field of characteristic is 0, and if A is a UFD of dimension 3, it's a K algebra also, then spec A is isomorphic to A3 if and only if it has a free G action and the Makar-Limanov invariant is trivial. Okay. So if you remember, for A2, the only this thing was not needed. Only Makar-Limanov invariant is trivial was enough. For A3, they show that we need a free G action. So G action, Makar-Limanov invariant, these things are same kind of things. And then there's this geometrical property, algebra topological and geometric property, of Miyanishi. A non-singular affine complex threefold X equal to spec A is isomorphic to A3 if and only if A star equal to C star, A is a UFD, sorry, A is a UFD, H3 exact is 0, so the third homology is 0, and there exists a non-empty open set U inside X such that U looks like V times A2, V is a curve, V times A2, and X minus U has non-singular irreducible component. Okay, so it's a union of non-singular. So it does not say anything about whether they intersect nicely or not. So it is not at all the thing, but at least each component is non-singular. That is the main thing. So Miyanishi gives this mixed kind of characterization of A3. Okay. So now these two, if you stare at these two definition, these two characterization, you see that there are, I mean, they look like coming from completely two different world. And our goal, together with my student Biman Rai, our goal was to actually try to build a bridge between these two things, because I mean, algebra should talk with topologists, topologists should talk with geometers. So all of them should have a should talk same room, or at least inside the same Zoom meeting. So few results. So we wanted to relate Sing X with Macaulay-Limanov invariant, for instance. It will be a starting point. So our Zoom meeting room was this A1 homotopy theory, so that we can make arrangement for everyone to sit inside this room. So let's Sing X with Macaulay-Limanov invariant. Okay. So we defined a new invariant. So if you remember, Macaulay-Limanov invariant is not a good invariant in the sense that it is not functorial. So what we did, and but then what I mean, the invariant actually gave you, if we contract all embedded A1 GA orbits inside X, the variety we get, or whatever the scheme we get is their regular function is precisely Macaulay-Limanov invariant. So similarly, instead of uh, uh, instead of shrinking all G orbits, we shrink all rational curves inside it. So O chain X we define to be all regular functions here, such that f is constant on all A1 to X, so all rational curves on X. So this actually turns out to be is functorial on X. In fact, it is homotopy invariant Quichev. So homotopy invariant means that it does not see any difference between affine line and a point. But then you can ask, okay, it's homotopy invariant. So does it come from A1 homotopy theory? And the answer is no, it is not a sheaf, or even not comes as any motivic invariant. And we managed to show that O chain X is isomorphic to K. So this will be again sheaf of K algebras, or sheaf of K algebras. So O chain X is isomorphic to K if Sing X is connected, or Macaulay-Limanov invariant is trivial. So we managed to uh, put everything in, at least try to make connections with each other. So this is then the open question is, of course, before going to this, the open question is, of course, does there exist any scheme, smooth scheme X, such that O chain X is isomorphic to K, but Sing X is not connected? So again, potential counterexample can be Ramanujan surface. At least for curves, there are no other example, but Ramanujan surface can be a potential counterexample, and Ramanujan surface you can. So there are we are trying different methods to actually prove that Ramanujan surface actually gives you the counterexample here. And then the theorem that we managed to prove is again a theorem which actually keeps both things, that topology, geometry, and G action, all of them together. So X be a smooth affine complex threefold. X is isomorphic to A3 if and only if X is topologically contractible, chain connected in the sense that Sing X is connected, that is, it has pi 0 is, so any 2 points can be joined by chain of affine lines, and has a free G action. So free G action, topologically contractible, and chain connected. All these things together will make X to be isomorphic to A3. So then the question will be, can we use this to prove cancellation or disprove cancellation? So sadly, the main thing is that if X, even if X does not have a free G action, X times A1 will always have a free G action. So having a free G action is not a homotopy invariant property. Okay, so this is actually a very important fact. Of course, topologically contractible is a homotopy invariant property, and of course, being chain connected, but having a free G action is not. So this is the reason why this characterization cannot be used to prove or disprove. Uh, Maybe to disprove you can use, but to prove cancellation you cannot use this, and that actually shows that there should be, the cancellation should not hold. So this property that has a free G action actually tells you that G action, having a G action is not invariant under taking product with A. So this is the end of the talk. I mean, I think that I have gone too fast, but yeah, I mean, I cannot actually, using my slides, I cannot like control myself after some time. So thanks for your attention. Maybe.
Thank you. So it was very nice. Thank you. So if anyone has questions, please ask now. You unmute yourself and ask. Okay. So yeah. So thanks, Utsav. Very nice talk.